Hey guys, taking a look at section 8.2 in AP Statistics. We are estimating a population proportion today. In the previous video, we looked at what confidence intervals were conceptually and a little bit on how to actually compute them. But today we're going to be spending a lot of time talking about how to do a confidence interval to estimate a population proportion. Quite a few objectives here we have. We're going to talk about the conditions in order to perform these confidence intervals, or for most types of inference for that matter. We're going to talk about how to find the critical value, the z star, for these confidence intervals. We're going to construct and interpret the confidence interval. And then finally, we're going to spend some time talking about sample size required to keep a margin of error within a certain range. Let's say we were trying to do an example. Now, this example might be one like something we do in class, but let's say I had a container and it had different colored beads in it. And your goal is to figure out the actual proportion of red beads in the container. Well, what would you do? You would want to try to take a bunch of beads and try to have it be as random as possible so that you can meet your SRS condition and therefore have confidence in your findings. You would then come up with a point estimate, something that we talked about in the previous section. The point estimate in this case would be p hat, the estimated proportion of red beads, and then we could find the 95% confidence interval for the true parameter p. And as we go through this video here, we're going to be talking about how we would actually do that. Now, let's just say we did this and we ended up getting 107 red beads and 144 of a different color beads. That would make our p hat, the number of reds over the total, 107 out of 251, or 0.426. How can we use this information to find a confidence interval? Well, this p hat, that would be our point estimate. And what we would need to do then is we need to say, okay, let's talk about our conditions. Do we have an approximately normal distribution? Well, if I did n times p and n times 1 minus p, using the 251 as n and this 0.426 as our estimate for p, we don't have a true p, so we're using this p hat, then we could say that they are at least 10, and therefore it is approximately normal. The mean of the sampling distribution of p hat is going to be p, so we can use that as our mean. And the standard deviation, as we talked about previously, is going to be the square root of p times 1 minus p over n. But since we don't have p, we're going to have to use p hat to estimate that value there. And hopefully it's going to be pretty close to the actual standard deviation that we would find. But again, since we don't have p, we have to use p hat in order to find this here. Just a reminder on the conditions. We said in class that it's a sin to forget your conditions. What does the S, I, and the N stand for? The S stands for the data is collected randomly. The I is for independence, and that means that you have your population is at least 10 times the sample size, or your sample is less than or equal to 1/10 of your population. And the N stands for normality, also referred to as the large counts condition. And in this case, since it's a proportion, the normality check is n times p and n times 1 minus p equaling or greater than 10. And again, notice that in this case here, they're p hats because we don't have a p to use. So we talked previously about the form of a confidence interval, and we said it's a statistic plus or minus a critical value times the standard deviation of a statistic. Now, the standard deviation of the statistic, sigma sub p hat, is square root of p times 1 minus p over n. But in this case, since we're using this p hat as an estimate, we have a new definition here, this standard error. And it's something that's going to be used a lot moving forward. So if you're using the estimated p hat value instead of the p, the standard deviation is referred to as standard error, or SE, of the sample proportion. And there's going to be a little bit more variability that goes into this, obviously, but this is the best we can do. We don't have any other information to use. So again, it says when the standard deviation of a statistic is estimated from the data, the results are called the standard error of the statistic. So as long as our conditions are met, then we can go ahead and talk about constructing our confidence interval. And let's say we wanted to construct this 95% confidence interval. Well, we said previously, if we want to construct a 95% confidence interval, then the critical value is 2. And you can find that using either your z table or the calculator, or in this case, it's easy enough because it's just 2 standard deviations away from the mean. But that's actually an estimate as well, because if you actually look at this value here, the z star, or the critical value for a 95% critical, 95% confidence interval is 1.96 or negative 1.96. It doesn't matter whether you use the positive or the negative. Now, if we wanted to find a critical value, say, for an 80% confidence interval, well, that means that we have 80% in the middle of the normal distribution and 10% in the lower tail, 10% in the upper tail. So if we wanted to find that critical value using the table, the z table, then we would be looking for where I have 0.1, and as I look, it's between these two values. So that means that my z star, my critical value, is between negative 1.28 and negative 1.29. All right. Now, in this case, you can just estimate and say, well, since 0.1003 is closer to 0.1000, then you can just use the negative 1.28. But if you wanted to be more exact, you could, bear with me a second here, you could use your graphing calculator. And if you're looking for an 80% confidence interval, then you can just go ahead and use inverse norm, which is in the second vars menu. And if you're looking for the area being 0.1, in other words, 10% to the left of that critical value, since this is a z star, the mean is 0 and the standard deviation is 1. So I can leave those defaults there. And you'll see I get negative 1.28155, etc. And that's very close to the negative 1.28 that we estimated from the z table. If we wanted to find a different critical value, say I wanted to find a 90% confidence interval. Well, if I'm talking about a 90% confidence interval, that leaves 10% total left over in the tails, but only 5% in the left tail. So I would put area of 0.05 there. Mean is still 0, standard deviation is still 1, and I could get that critical value of negative 1.64485. So these are some common critical values that you're going to be using in your confidence intervals. So those are ones that you want to look out for, but we'll practice that more in class. All right. So, but the key here is that the critical value of z star for an 80% confidence interval is going to be 1.28, or a more exact 1.281. So if you wanted to construct a one sample z interval for a population proportion, it's going to take the form of a statistic plus or minus the critical value times the standard deviation of a statistic, or standard error. And again, there it is in this form as well. So let's go ahead and do one, but in this case we're going to do a 90% confidence interval. And for this same example that we talked about at the beginning of the video, where we had 107 red beads and 144 beads that were a different color. Now, it says the teacher claims that 50% of the beads are red, and we want to construct a confidence interval and then comment on that claim. So we already went through on the calculator to find what that critical value would be, but here's how you would find it using the table. Because I'm looking for 0.05 as my area in the left of the normal distribution curve, I see that these two values are equidistant from 0.05. So I could say the critical value we would use would be negative 1.65, negative 1.645, excuse me. Now, as we look at it here, we can then plug in and say, okay, the p hat that we had was 0.426 plus or minus 1.645. That's the critical value. And this 0.426 times 1 minus 0.426 over 251, that's the standard error. And then we can just plug in and we get 0.375 to 0.477. If we were to interpret this confidence interval, we would say we are 90% confident that the interval from 0.375 to 0.477 captures the true proportion of red beans in the container. Not 100% of the time will it contain it, 90% of the time. Now, keeping in mind that the claim was 50%, if I look at this confidence interval, it does not include 0.5. So it says, since this interval gives range of plausible values for p and since 0.5 is not contained, we have reason to doubt the claim. It doesn't mean the teacher's definitely lying. If when we construct a 90% confidence interval, 10% of these confidence intervals won't contain true proportion. But it is evidence that they are not telling the truth, excuse me. If we were to change this to a 95% confidence interval or a 99% confidence interval, there's a chance that it would contain 0.5. But for now, we do not have it contained. Now, that was kind of an informal way to go about the problem. We talk about in statistics something called a four-step process. And the four-step process is a very specific, a very formal way to go through and actually conduct a confidence interval, or later on, as we'll talk about, a significance test. So what does it look like? Step one, you're going to state the parameter. What is the parameter that you're trying to estimate, and what confidence level are you using? So we'll say we're trying to estimate P, the true proportion of red beads in the container. And we're doing a 90% confidence interval. Plan, identify the appropriate inference method. So in this case, we're talking about a 1 proportion Z interval. That's the phrasing that we use for this confidence interval. And you would also, in this step, check the conditions. SRS, independence, normality. And then in step 3, as long as the conditions are met, you're going to perform the calculations. The point estimate plus or minus the critical value times the standard deviation of the statistic. And then you're going to interpret that interval in the context of the problem. Very, very critical that you keep it in the context of the problem. Now, a little bit about the sample size. Sometimes you want to be really careful about how large a sample you use, because you don't want to end up having a confidence interval that's too large. If you're trying to estimate the amount of money that you're going to spend in a month, you don't want to have that range be, say, from $1,000 to $4,000, because that's a very big range and it doesn't really help you in any kind of planning. You'd like your confidence interval to be as narrow as possible, but still have a high level of confidence to go along with it. With that in mind, there are ways to control the width of the confidence interval, in other words, the margin of error, using some quick analysis from the confidence interval formula. So we know the form for the margin of error is equal to the critical value times the standard deviation of p hat times 1 minus p hat over n. Sorry, the square root of p hat times 1 minus p hat over n. Now, the z star, that's your critical value. And what we're trying to do is we're trying to control this margin of error. So we are going to have a z star. Now, the p hat, this is the interesting part here. We've not actually gotten our data yet. So we don't have a p hat. So we're going to be estimating that p hat. And there's two ways to do it. First, you can guess a p hat from past experience or a pilot study. So if you know, or if you believe that 20% of the time you're going to have a success, then you can go ahead and use 0.2 as your p hat. But if you have no idea what kind of data you're going to have, just go ahead and use 0.5. And the reason you use 0.5 is because that's the safest value that you could use, because it's going to give you the largest margin of error. And what that means is it's going to give you the most conservative margin of error. Therefore, you have confidence that even if it's not 0.5, then your margin of error will still be within what you want it to be within. So how do we go ahead and do that then? Let's look at this example. It says a company has received complaints about its customer service. Managers intend to hire a consultant to carry out a survey of customers. Before contacting the consultant, the company president wants some idea about the sample size that she'll need to be required to pay for. One critical question is the degree of satisfaction with the company's customer service measured on a 5-point scale. The president wants to estimate the proportion of customers who are satisfied, that is, who choose very satisfied or satisfied, the two highest levels. And she wants to be within 3%, in other words, 0.03, at a 95% confidence level. So at this point, we have a lot of information. The fact that it's a 95% confidence interval tells us that we can find our critical value, our z star, and it should be 1.96. We know the margin of error is going to be 0.03. We are not given any p hat to use, so we're going to have to use the most cautious value of 0.5. And we don't have n. That's the whole point. How large a sample is needed. So let's go ahead and plug in what we know. All right. Critical value, 1.96. Don't have a p hat, so use 0.5. And the margin of error is 0.03. So we say the margin of error has to be less than 0.03. So we plug in what we know. Here's our 0.5 value. And then at this point, all we're really doing is just a little bit of algebra. So if I were to try to solve this equation here, start by multiplying both sides by the square root of n and dividing both sides by 0.03. So from step 1 to step 2, we isolated the variable. But it's not exactly isolated because we also have to come in and square both sides because we don't want the square root of n. We want what n is. So you square the left side and you square the right side. And at this point, we have this arithmetic over here. We just go ahead and simplify that. And we get n, if I read from right to left, n is greater than or equal to 1067.111. But we can't have 0.1 of a person, so we say at least 1,068 respondents to ensure the margin of error is no more than 3%. So obviously some things could change in here. We could have a different level of confidence. We might know what the p-hat might be, or we might actually want a different margin of error. But the everything else remains the same as far as just solving the algebraic equation there. So that's it. We talked about our conditions. We talked about finding critical value. We talked about constructing and interpreting confidence intervals. And we talked about sample size required to obtain a confidence interval with a margin of error that is specified. That's it. We'll see you next time.